Every once in a great while, someone comes along and notices a pattern that no one had noticed before. The point might be, for example, that the planets in the solar system obey precise and relatively simple rules. Or it might be that the spectral lines of hydrogen obey a simple formula with uncanny precision. Perhaps it's a similarity between the flight of a cannonball and the orbit of the moon that catches someone's eye. Or it could be an arrangement of subnuclear particles that suggests their inner workings. Insights like these are never mere flashes of inspiration. They're the result of endless labor, trial and error, outright mistakes, and half-seen truths. And often, once accomplished, they become the subject of bitter controversy over who gets the credit. But this much is never in dispute. Once a new pattern has been discovered, and one part of the universe has been connected to another, the connection will never be forgotten. Such events are never the end of the story. Often, they're just the beginning. But what they begin may be nothing less than revolutionary. The tale of the mechanical universe began with the scientific revolution. Tired of the unwieldy complexity of ancient astronomy, Copernicus took the Earth from the center of the universe and put it in its place under the influence of the sun. And when the dust had settled, the result was a totally new view of the universe as a machine. A wondrously complicated machine, but one that followed precise mechanical laws. Knowingly or not, that idea is the silent foundation of all Western thought, from the time of Newton up to and including the present. But ironically, it's no longer believed by the very people who invented it, the physicists. And so the tale of the mechanical universe ends with the story of a second revolution. A revolution that occurred in this century, almost within living memory, and one from which the dust still hasn't settled. As with the first revolution, the second grew from an attempt to solve a problem. The first solved the problem of the solar system, and the second solved the problem of the atom. Could it really be that two such similar problems would require such radically different solutions, so that a second revolution would be required to overthrow the first? After all, the first revolution, the invention of classical mechanics, had not only solved the problem of the solar system, it had accomplished a great deal more. To begin with, it seemed to reduce all the phenomena in the heavens and on the earth to a single equation, a vector equation to be exact, and a vector differential equation at that. But within its scope, it held the answers to a startling variety of questions. What's the principle of keeping perfect time? Or the secret of steering an infallible course? Why do ocean waves break on a beach? And why might a sturdy bridge collapse? With answers to questions like these, classical mechanics itself seemed to be a structure that would never collapse. Instead, it would inspire and guide the exploration of new realms. And in the long run, no expedition would be more fruitful or strike with greater force than the study of electricity. Ben Franklin, with his seemingly endless talent for invention, gave the first useful account of electric charge. And with it, he provided the first explanation of a phenomenal 18th century invention called the Leyden jar. Of course, Michael Faraday was separated from Benjamin Franklin by a revolution, although not one of the scientific kind. Still, Faraday and Franklin did have much in common. They shared an almost perfect innocence of mathematics, an insatiable curiosity about nature, especially the nature of electricity, and a very considerable share of genius. And that's just what it took to connect electric charges with lines of force. The concept of lines of force would encompass magnetism just as well. And when Michael Faraday confronted the question of how magnetism could be used to create electricity, his answer, electromagnetic induction, would put the world in a constant state of changing flux. No one grasped the significance of changing flux better than James Clerk Maxwell. Maxwell had both a secret and a dilemma. The secret was that hidden within the forces between electric charges and the magnetic force between electric currents, nothing less than the speed of light itself was waiting to be discovered. The dilemma was that for all the elegance and power of the laws of electricity and magnetism, the laws of Gauss and Ampere and of Michael Faraday, there was something missing. And when James Clerk Maxwell supplied the missing piece, the idea that changing electric flux would produce a magnetic field, he had not only illuminated the entire electromagnetic spectrum, he had completed the science of electricity and magnetism. It was an accomplishment that rivaled Isaac Newton's invention of classical mechanics itself.